Good afternoon, everybody. Yeah, we have this nice lunch, but still I want to give you some more insight in the work that I'm doing now. So, say 8 years ago, I really stepped away from the liver failure world, among others, because I moved to the US and started to work more on sarcopenia, muscle loss in a variety of clinical diseases. And for that, I had to develop, in my opinion, a lot of new stable isotope approaches in humans. And that is what I want to show you today. What is possible now and how was it in the past? So it's a kind of fancy name, of course, targeted fluxomics. Because what you do is you measure the flux of specific metabolites on a whole body and an organ level. And targeted is that you focus on specific metabolites and processes. But again, actually, that's what we did all our life, but it's just a fancy name. It has a new name. So I will show you what's possible in this field and what we did in many years, but also the real new stuff here. Just to start with this basic idea. These are studies that we did in pigs with acute liver failure. And very clearly, if you induce acute liver failure in this pig, you will find that the plasma arginine level goes down very quickly. So then you would say, okay, it is arginine deficient. We have a problem. Shall we correct this arginine deficiency? My point is and was, you have to measure actually whether there is not enough arginine produced. Because the plasma concentration actually doesn't relate to production or consumption, it relates to the clearance. And that's a mistake that a lot of people make. So we measured in these pigs the actual production of arginine in the body. And that is not different at all. So although the plasma concentration is very low, there is no change in the production of arginine metabolism. In the same time, the precursor of arginine in the body actually goes up in concentration, like all amino acids, which then in the body is converted to arginine. So there is indirectly some arginine that is supplying this pool. It's not enough. But the real issue is that this reduction in the concentration is just that the clearance, say the capacity of the body to clear the arginine, has increased. So what would we learn from these data? So lower arginine, unchanged production, also an increased production, but is there truly an arginine deficiency? In other words, would these data be sufficient to say, let's try some intervention with arginine in liver failure and let's see what's coming up? As an example, how important these approaches to measure turnover with stable isotopes are to really define what's going on. Other studies that we have done for a long time is looking at the effect of when people have blood in their stomach because of a bleeding in liver failure. And very characteristic, you see that the concentration of one essential amino acid, isoleucine, is actually reduced a lot. The reason for that is very simple. Blood proteins do not contain isoleucine. Biochemists don't understand it, but it's actually true. It is a complete protein lacking one essential amino acid. But we have struggled all the time. Okay, what's next? How is this important? These are, I think, very nice studies that are done in Edinburgh with Rajiv and others, of course, in which we measured the actual protein synthesis of the liver in healthy subjects. And there were reasons why we could do that. And this is in a normal situation and a control balance. But here we have added the missing isoleucine to this meal and found that it clearly stimulated the protein synthesis in the liver. With other approaches, it would almost be impossible. So these stable isotope infusion protocols, the fluxomics indeed, gives you a true information. So if you add it increased, and we found it is mainly in the liver. And then the hypothesis is still there, but I think it's still not a lot of people are doing this during bleeding, but actually if you would infuse isoleucine now in a patient with a bleeding, you would actually improve the quality of the protein that they eat and by that they will have a high anabolism. Actually, it would even improve their muscle mass. It's actually very interesting to think about. But again, this is information which you can get from these isotopes. One step more that is done is measuring across organs, and that was the favor of me for a long time. And then I met Rajiv, and he said, "Oh, no problem. Oh, we have a catheter. Oh, a renal? Okay, well, let's do a renal." So we were really able to measure what's going on in the cirrhotic patients. And it gives insight in how metabolism is going. This, for instance, is the ammonia production or consumption. So here you see that the portal drain viscera, the gut, produces ammonia. So in human, this is true what we know from animals. That also, most of the ammonia here is actually consumed by muscle. That also fits, so we know this now. And, which is interesting, is that the liver has a certain role in that. First of all, that depending on the portal systemic shunting, there is either a release or a retention of ammonia. So the portal systemic shunting actually decides how much is released to that. If you would assume that the splanchnic area is not too much shunting, then the immediate next organ that produces ammonia is actually the kidneys. So that gave us all the idea. This trans-organ measurement gives information that we really underestimated the role of the kidney. In other words, this is the consumption of glutamine. We show that glutamine is a precursor. Where is this taking place? It's taking place, of course, for a large part in the portal vein viscera. But this, I think, is very nice. You can look for the different blood vessels like the superior mesenteric and the inferior mesenteric, the splenic and the left gastric, that most of the ammonia is produced in the small intestine, which fits again with our physiology. So these trans-organ studies really give you new work. And it also improves your understanding. Rajiv, this is so nice with the cooling. If you look pre-cooling, you see that the ammonia is taken up by the brain, while the glutamine, and it's on the right axis, is produced. By cooling this individual, this ammonia uptake almost is zero and stays zero for a long time. So this is a direct proof that the cooling has a substantial effect on the ammonia and glutamine metabolism in the brain. Other studies we've done in Maastricht shows that, and we got an interest in arginine metabolism, that there is a clear pathway from glutamine all the way up to arginine. Glutamine is consumed by the gut. That leads to a production of an amino acid, citrulline, that is taken up a little bit by the liver, but in total is produced by the splanchnic area, that's taken up by the kidney, and finally arginine is produced. Again, very nice information on trans-organ studies. This other study has to do with this blood meal intervention, and better shows that it's actually the increase in the renal ammonia production when you give this blood meat. So we learn a lot of physiological information by going into this flux measurement. This is some recent work to see how we can advance. This is more in a critical ill situation. We published in 2007 that although, in contrary to everybody's belief, that ICU patients do not have a higher NO production but actually have a lower NO production. And that's very clear. So this is a control. These are ICU patients that were on their way out to the ward, and these are very critical ill sepsis patients. So septic patients have a reduced NO production. That led us to go after, should we give arginine to critical ill patients? And we did that in ICU patients, very severe, Apache above 20. We started to infuse arginine in 3 different levels. No infusion, a lower level, intermediate level, and a higher level. And this is the plasma concentration that went on. By using our stable isotopes now, we could really prove that the NO production indeed is stimulated when you infuse arginine. In other words, by infusing arginine, you can normalize the NO production in patients. Not shown here, but there are absolutely no hemodynamic effects of infusing arginine in ICU patients. But what's very interesting at the same time by using the isotopes, actually the arginine infusion led to a reduction of the protein turnover. So there is a link with arginine and protein turnover. So what can you learn from this in septic patients? Of course, that you can stimulate NO production, reduce protein breakdown. It has no effect on the several other things. And so at the end, you can, in fact, we still are dealing with, is this good or is this bad? This is a kind of very small overview on what you can do in human settings. But again, I told you I went on. I went to new approaches. The first thing I wanted to know better the response to nutrition. I want to know whether this supplement or that meal is better for this patient or for that patient. So in relation to this field, what is the response of a patient with liver cirrhosis to a meal? Are they less anabolic to this meal? Or do you need to give a specific protein meal with specific proteins? That seemed to be a very elementary question, but very important. Or which ones of the dietary proteins are the most anabolic ones? Or, and this is a new development, is there actually any effect of protein digestion capacity in liver cirrhotic patients, which could link to the microbiome actually? The other wish that I had was, if I want to advance my field, it should be with methods that everybody can apply. I should not have a setting where it's too complicated. So I really went to the techniques and looked for methods that are really simpler and more easily to implement, and that every physician that I worked with could actually implement in this institution. So we went on. Can you measure tissue protein synthesis in a muscle, liver, gut biopsy within 1 hour? When you have only one catheter available in your patient, and we had that in certain circumstances, what can I do if I have to use the same catheter for infusion and sampling? Is there something that you can use? Or even better, can I measure metabolism without those difficult, unreliable infusion pumps? Or how much of the food that I gave is actually digested or absorbed? Or, what is also very important, how is the effect not in 2 hours, but in 3 days or in 2 weeks? That are all very critical questions, and I have an answer on all, of course. First, I want to show you what we did a lot is how can you estimate the response when somebody eats a protein, a carbohydrate meat, the net. This is the way we do this. We do this now on an almost daily basis. We do, for instance, you want to compare one protein to the other. We do that between days. Patients come in, the subject come in the morning. We start with a prime constant infusion of stable isotopes. We wait a little bit, then we give one meal. We take a lot of blood samples, and after 3 hours, we are done with this study. That's the first approach. What do you need for this approach? You need arterialized venous blood. You need, of course, methods to analyze. And you can calculate the protein synthesis breakdown on the meal, the protein breakdown, the net synthesis, and that's the number that you actually want to know. And you can also estimate the splanchnic extraction, how much of the food is actually retained. And the protocols that we use are phenylalanine and tyrosine tracers. And we add, and that's very important, also isotope to the meal, so we can establish exactly how much is extracted. This is the kind of data you get. So this is the phenylalanine tracer that we infuse, nice steady state. You give the meal, the enrichment goes down because it gets diluted by the meal, and then for a while it normalizes again. This is, for instance, the concentration of phenylalanine. But, and that's the nice part, this phenylalanine is converted to tyrosine. So you can measure the conversion rate to this tyrosine. Note that these are enrichment around 10%, and here you are below than 1%. So that's the only requirement that your machines very well. This is the other tyrosine that you infuse. This is what's in the meal. So you see it comes up when I give the meal, the 15N phenylalanine, and you even have the conversion to tyrosine. With these data, you can calculate. For instance, as a very recent example, we measure the splanchnic extraction of the food that we give to a patient with COPD, another chronic disease. I think not so different maybe than cirrhosis. And we see that these COPD patients very remarkably are characterized by a lower splanchnic extraction, which means that actually everything they eat probably is more available to the muscle. And that's true because the changes in the plasma concentrations are higher when you give exactly the same meal. It's a very interesting concept. But with this method you can also estimate what is the response of the muscle, of the peripheral tissue, of what's available. And this is what we call exogenous phenylalanine. And then we make this curve with the net protein synthesis, and we have published several other papers now that show that there is a very nice linear relation. In other words, protein synthesis in the muscle actually relates very well with the delivery of amino acids to muscle. It's very important. And there is no difference at all between healthy males, females, and COPD males and females. Actually, in this study we show that the higher the concentration, the better the net protein synthesis. This is new style of information. Suddenly you can test whether this protein meal is better than the other protein meal. And because of this difference in splanchnic extraction, for instance, these COPD patients actually respond more anabolic to a meal. How odd is that? But the same amount of protein is used more in a COPD patient than in a healthy. So besides this, these studies have learned a lot. First of all, protein anabolism to a meal relates to the amount of essential amino acids in the meal. I will show you that later. That the splanchnic extraction, which is important in cirrhosis, actually determines your anabolic response to this meal. We found even a direct relation between the synthesis and availability. And how can that be, that they are more anabolic during a meal? This immediately points to the situation that they are probably more catabolic when they do not eat. And think about the cirrhotic, that's maybe what's going on in these patients. So you have to look maybe in cirrhosis in the same way. Or maybe we should test meals with only essential amino acids because they have probably the highest quality. And for instance, you can deduct, if that's true in cirrhosis, that you have arguments again to give these people more than one meal. The same is true in cancer patients. We test very stage 3-4 lung cancer patients, and we found exactly the same relation between how much is available and what is the net protein synthesis. Very important here is that we tested also a mixture with a high amount of leucine, but there is no effect of the leucine at all in this test. It's only determined by the amount of essential amino acids. So it's only essential amino acids, no effect of leucine, and the protein anabolism depends on the amount of essential amino acids. Maybe our liver cirrhosis not anabolic resistant, and maybe they respond more than healthy subjects, which means that we can go for the meals. Now this is new style and type of information that can be very helpful. When I did these studies, the first thing with the COPD thought, there's probably a problem with the digestion. That makes maybe this problem. So I thought about it, and we developed and published a new method to measure digestion of protein. It's actually very simple, but okay. The idea is the following. If you give a meal with protein, these proteins need to be degraded to amino acids before they can be taken up, say in red. If I would give pure amino acids, they will be taken up without any digestion. So what we did is we labeled the protein by using a completely labeled protein available, which is spirulina protein, and we added a free amino acid. And the trick is, if you know the ratio between the two isotopes when you give it, and you measure it somewhere in plasma, you actually have digestion. In other words, if the ratio is unchanged between what you give and what comes out, then you have 100% digestion. If you find a half, you have 50% digestion. But I needed to test whether this is true. So we went to our cystic fibrosis individuals who have pancreatic dysfunction, and we tested both in adults and in children. And this is digestibility. So in these patients, their digestibility is about 50%. So these CF patients cannot digest protein very well. But then, of course, we gave pancreatic enzyme, and you see our parameter nicely responding to the pancreatic enzyme and normalizing and actually going back again. So this simple approach, by giving a certain meal, actually you can now measure digestion. So this is I think it's very interesting, and it gives a lot of attention in the CF world, because you can also see that it takes some hours before it actually starts to work. And they had the idea that it immediately works, the pancreatic enzymes, but it's not actually. And you can measure it every 15 minutes or whatever you want. My view in this world is it could well be that cirrhotic patients also have a problem with their digestion. That could well be. And should you not do that, maybe that's an indirect way of the reason why they have malnutrition, because their proteins are not very well taken up in relation to this morning. So there will be more protein in the colon that will change your microbiota, and that's what you're looking at. That could well be a hypothesis to work with. Because it's just digestion, I started to work on absorption, with the same idea. And what I use is a particular amino acid, which is called allo-isoleucine. It works like isoleucine, but it's a little different. But using stable isotopes, 2 different forms. And I also try to develop the same principle with D amino acids, and also using the labeled one. So the allo-isoleucine is very interesting. It's absorbed at the same rate as isoleucine, but it's not used in protein synthesis. And for that, you can use a ratio between the two. For instance, here we tested it first in a pig model, so the absorption quickly goes to 1. And then, for instance, we start giving food, and then the absorption goes a little bit down. So this is what we are developing now with stable isotopes. And you can do it in your regular measurement, because these isotopes do not interfere with your normal isoleucine measurement. But it measures the absorption of amino acids. And with the D amino acids, you can do the same. It's the same idea. And for instance, we gave a pulse here of a D amino acid to see how many L amino acids come out of it, and that's very low, so that's usable. So absorption is also possible, and that you can combine with measuring digestion. So, and we measure splank extraction, so you have a panel that gives you information there. Some other. We are all interested in protein synthesis, but sometimes it's hard to measure. This is what we did together with Chris Rose when he was in Little Rock, and we had this idea. If you measure protein synthesis in a tissue, it's a relation between how much isotope is available versus how long do you, after that you take a biopsy, and then you measure synthesis. But if you want to do it well, you actually have to take 2 biopsies, or maybe even more. There is a new trick, and that's called pulses. If you give a pulse of amino acids, like here, this is the plasma curve, you actually just need the area under the curve of this to be able to measure protein synthesis. The trick is that you give another pulse of the same amino acid but with a different isotope, and another pulse of the same amino acid with a different isotope, that actually with one biopsy you can exactly show the curve of the enrichment in the tissue and in the intercellular fluid. So there is a way to measure protein synthesis by giving 3 pulses timed, and this is in total 1 hour. Think about it doing the same. I have a patient on surgery and I want to measure liver metabolism. You give 3 pulses, they take the piece of tissue, and you have the synthesis. And the nice part is, if you have a problem and you have to wait until 70, until 80, that doesn't affect these data at all. So it's even not time critical when you start taking the sample. So with Chris, we did this with bile degradation rats and sham rats. And he measured, and he took all tissues, brainstem, cerebellum, frontal cortex, all those stuff. And these are this protein synthesis in all these tissues measured in one setting. We have to work, of course, more on that, but this, I think, is a very nice new approach to be able to quickly measure the synthesis. And for this, for instance, you really look for the muscle, how low the muscle synthesis is. These pulses can be used also for other things. We will also measure the synthesis rate of glutathione. It's the same principle, just add glycine to the pulse. And you can even measure the fractional protein breakdown rate by the same idea, because if you have the intercellular enrichment and the plasma enrichment, you can calculate the fractional breakdown rate. This was a study that was done in Little Rock in patients with hip replacement surgery giving an essential amino acid mixture. These are the curves for the first pulse and the second pulse. So this was a 2-pulse study, and then you had to take 2 biopsies. But as a principle, the synthesis is increased by the essential amino acids, but not that much. But what I think is really more important, the protein breakdown is substantially reduced by giving the amino acids. So if you have both synthesis and breakdown, that's even better. And all applicable to the cirrhotic situation. So these pulses are very interesting. Remember, if you give a pulse of isotopes, you don't need a pump. You just need one catheter. You have a weight syringe, say in a human 10 ml. You give the pulse, you flush the line, and you take samples. That is what you can do with this. Now, first I showed you these prime constant infusion things. So you prime it, you have it at a constant infusion. But if you give a pulse, the enrichment has a certain pattern, which you can fit, of course. And from a model point of view, this is actually very interesting, because by doing the pulses, you actually can get information not only what's happening in the plasma pool, but also what's happening in the tissue. And you can do some easy compartmental modeling and actually measure the true intercellular protein breakdown, for instance. So this we did in a pig with sepsis, and the green is the control, and the red is the septic pigs, and we compared the constant with the pulse to be sure that it gives the same information. And the pulses do not change the concentrations, that's very important. This is by the prime constant infusion, so sepsis leads to a higher protein turnover. And if you use the pulses, you will find exactly the same, although the number is higher because it better represents what's going intercellular. So these pulses without infusion pumps within an hour gives you exactly the same information than a 3-hour system with priming and all that problematic thing. And it gives you more information because you actually can measure the intercellular protein breakdown. I think that's very critical. And I will not go into detail, but it relates very well with all the other things. So we published this, for instance, this year, and explaining the compartmental analysis of the data, but again, it's not so difficult. And in this case, we measured citrulline production in a CF patient to see whether they have disturbed gut metabolism. Again, also in this human study, you can find the same type of information from the pulse that was given, and also here you find a reduction on the whole body level of breakdown. I moved on with this pulse. I think you should all be very interested in that, because you have one syringe, you can add 2 isotopes, you can add 10 isotopes, you can add 20 isotopes, there's not a problem. So at the moment, our pulse looks like this. We have phenylalanine, tyrosine, leucine, KIC, metal histidine, a long list. And besides measuring the production, we now measure protein synthesis and breakdown and net breakdown in this pulse. We measure actually the leucine transamination and reamination by the combination of these two. That's new type of information. We measure muscle-specific protein breakdown, myofibrillar protein breakdown, by adding this metal histidine tracer. We measure collagen protein breakdown, which would be nice in fibrosis, by adding this proline tracer. Glutathione synthesis, NO production. We measure the glutamine transamination, reamination, I think for others very interesting. Urea, of course, etc. So for instance, this is the urea pulse, and you see that goes very quickly. This is citrulline, arginine, etc. So these pulses are really a new approach that you can do. You get better information, I believe, and for instance in our field, acute liver failure, you can still measure NO production, protein breakdown, etc. and etc. Last part. Is that okay, Chairman? Okay. So I gave you new approaches. The last one I think is very interesting. In the past, people did experience with heavy water, heavy labeled water, D2O. And we were always afraid of giving D2O, and the tracer goes everywhere. Now, I think we now know where it's going, and I think that's an important point. If you drink heavy water, the water in your body becomes enriched, and those proteins will go everywhere. That's true. But for instance, in the fat world, these deuteriums actually will label fatty acids. So by taking a fat biopsy, you actually can measure the synthesis rate of fat in fat tissue. By looking at plasma fatty acid, you can estimate the production of fat in the liver. So by not infusing at all, just giving this heavy water, you can follow fat metabolism. And this is what we are now doing, and it seems to be very interesting. But besides fat, it also starts to label protein, glycerol, glutathione, an enormous amount of, actually all substrates starts to become labeled. And you can use that. For instance, for amino acids, for alanine, for instance, both that the metal group deuteriums are labeled, also the 2 is labeled. And leucine is actually also labeled by now, glycine. So we are actually not so afraid anymore by using D2O in combination with the others, because we now know where the label is, and we can actually measure where the label is. For instance, giving D2O will label all these amino acids in a different level, and it's very clear that the non-essentials, of course, have the highest labeling. So we can use that to measure fractional synthesis rate. And giving deuterium water, within 10 minutes the labeling in your amino acid is at a steady state. So you can use that, but also to measure the synthesis rate of plasma proteins, the ones that are made in the liver. And you can follow this for a long time by just taking 1 drink of D2O. I think this is very interesting, just out, and they follow this up. And they look for the enrichment in body water, which slowly goes down, because this is water turnover that you measure actually here. But you see day 8. They took a muscle biopsy in the beginning, at day 2, at day 4, and day 8. And by that, they could measure the differences between the enrichment of the muscle biopsy and have protein here, myofibrillar protein synthesis rate, for a long period, all the way up to 8 days. So if you want to do an intervention that takes 7 days, you will have an overall effect of the synthesis. I think that's very nice when using the D2O. And this is just summarizing all the things that recently are used. Cholesterol synthase, that's very old. Collagen synthesis can be measured with D2O. Breakdown also. Protein, of course. Specific peptides, if you have a specific peptide that you are interested in, by giving deuterium water and measuring the enrichment in that peptide, you will measure the actual synthesis of that peptide. Gluconeogenesis has been done a lot. DNA synthesis can be measured very well if you give deuterium water. Glycogen synthesis, glutathione, fat, etc. So what I hope and that was the reason why I was asked, whether these techniques that are available in other fields could be helpful in this field. We have this standard thing, the prime contribution, and you can replace it with the pulse. Very important. It makes it really easier. And we have cheaper also. D2O is very cheap. The pulse amino acid protocol, so this pulse of 10 ml with all those isotopes costs less than $50 in total. So your tracer cost is way down, and that's an important point. And I think very important, do not forget that we should measure also digestion and absorption. So thank you, and if you have any questions on your application, let me know, and I'm more than happy to explain to you if I think that there's something possible there. Thank you.
Very good.